And so I think there's at least a homework problem that talks about calculating that energy difference. You can calculate how much, so what does that energy go, right? When we lose that energy from absorption to fluorescence, what happens to it? It turns from light energy, radiant energy, into what?
Is it heat?
Yeah, it's heat, absolutely. So we move that vibrational relaxation, right? Those vibrations get that molecule moving. Moving is kinetic energy. And remember that temperature is just an average kinetic energy for a system. And so we do think about it as converting into thermal energy. And so not only could we calculate the difference between S0 and S1 based on the absorption of the emission, but we can also calculate how much thermal energy is gained by the molecule in that fluorescence process. Right? How much does it actually heat up? We could go that far if we really wanted to. If we knew specific heats and all this stuff, we could get there. I'm not interested in that. Okay. So that's Jablonski diagram. Again, we're interested in this S1 to S0 transition. And we get, sometimes it's called a mirror image rule. And so if we look here at part B of this image from our text, you can see that these really are pretty much mirror images of each other, the absorption and the emission spectrum. Again, absorption in black, emission in blue. Now, where does this sort of mirror image come from? Well, when we excite a molecule from the S0 to the S1, up to this point, we haven't talked about what happens to that molecule. But in reality, the way the electrons are distributed shifts a little bit, and that molecule can actually shift a little bit, change its conformation just a tiny bit. So think about a planar molecule. If you're an organic kind of person, think about a planar molecule. If you break the conjugation in that planar molecule, it may not be planar anymore, right? And so we have a shift in those in that conformation when we change the electronic state of a molecule. And so in figure A here, part A of this figure, you notice that our x-axis is nuclear coordinates. Now, in reality, writing Frank Condon overlap potentials in a two-dimensional graph is almost meaningless because, of course, this is only looking at a single nuclear coordinate, right? We can only look at two nuclei and how they shift in terms of distance. Often what they do is they sort of take an average movement and see how the average molecule changes. And so we have some shift. You can see this Q1 here. There's some shift in where that minimum is from the S0 to the S1. Again, I don't want to get into it too much, but because it shifts, that's why we get these different peaks in our spectrum. And so the ground state vibrational levels are built up here in the S0. The excited state vibrational levels are built up here in the S1. Oftentimes, those are very similar vibrational levels, depending on how much the molecule changes conformation. They could be very different if the molecule changes a lot, but if it's just a small shift, then the vibrational states stay the same. In order for electron to be absorbed, we have to have good overlap between the wave functions. That's a real quantum mechanical sentence I just said. But in the light blue here, what's being drawn, what's being sketched out are the wave functions for the molecule in that vibrational level. Right? And so for the S0 in the ground state, it's pretty centered, it's symmetric, there's only one hump. We say that there's 0 nodes. As we go up, of course, for a first vibrational state, there's one node, second, two nodes, third, three nodes, and again, where it crosses the x-axis, those are the nodes. And quantum mechanics tells us that in order for an electron to change energy levels, what has to happen is that the energy levels share some overlap. They have to share some density, we call it. And so if we look, going from 0 to 0, there's not a whole lot of density in that wave function way out here. In the v equals 1, there's a little bit there. V equals 2, yeah, man, that's what we're talking about. That's almost the highest density in the v equals 2 wave function. V equals 3, tiny. V equals 4, not too bad. V equals 5, there we go. We've got a good bit of overlap again. And we can see this in part B here, right? The 0 to 0 energy is very low because there's very little overlap between the two wave functions. And then 0 to 2, of course, is our peak because that's where the most overlap is. 0 to 4, 0 to 5 have some. 0 to 6 has a little bit. 0 to 3, not a whole lot. And so this Frank-Condon overlap, again, is just the wave functions do the wave functions overlap at a particular nuclear coordinate. Right? That's essentially that's the question we're trying to ask, right? That's going to tell us how intense the signal is for a given transition. Yeah. Maybe better than do is how much, right? How much do the wave functions overlap? Because they all overlap a bit, but the more overlap, the greater the intensity. And if we have a relatively little structural change, in other words, if our vibrational levels stay essentially the same, then the overlap that we see in the excitation, the absorption, should be the same overlap that we see in the emission, right? Our 0 to 2 is still the most intense in terms of overlap. It has the best overlap, and so you see that the 0 to 2 is these are backwards, by the way. Oh, wait a minute. They're not. Oh, gosh. Why would you do this? This is energy, not wavelength. That makes me go funny. Yeah. So, yeah. Going from the ground state to the excited state, we're going from 0 to 2. Going from the excited state to the ground state, we're going from 0 to 2. The reason those are different energies, right, is because in the excited state, 0 is lower than 2. Well, in both states, 0 is lower than 2. And so we have extra energy in the absorption, less energy in the emission. Okay. Questions about that? Again, that's just sort of what's required in order to have good absorption and good fluorescence. So if we look at a real molecule now, instead of just pretend ones, this is anthracene, this molecule here. And you see that this molecule has this mirror image . rule. Right? And again, that mirror image rule means that the excited state doesn't shift a whole lot from the ground state. Generally speaking, absorption will always be higher energy than your fluorescence, which means that the fluorescence will always be at longer wavelengths. So how do we explain this little bit in the middle where the fluorescence is actually higher in energy than the absorption? You may want to take a stab at explaining that. Okay. So in order for us to have some emission here, can we excite at that same wavelength? Yes, no, I don't know. What do we always lose in a fluorescence transition?
You lose some energy.
We lose energy. So if this is my fluorescence, can I excite at that same wavelength?
No.
No. So where do I have to excite? Higher wavelength, lower wavelength, if it can't be the same.
Low wavelength.
Yeah. So remember, these are spectra. These are not individual points. And so maybe this absorption gave me this fluorescence. And then we can tie some more points together. Maybe this absorption gave me this fluorescence, right? I don't know. I'm just saying. Right? And so, yeah, we can't lose energy. I mean, we can't gain energy in a fluorescence experiment, in a fluorescence transition, right? And so our absorption always has to be at a higher energy or a longer, shorter wavelength than our fluorescence is. Okay. Yeah, let's move on. So fluorescence quantum yield. This is a big deal when you talk to people who do fluorescence. This is essentially, right, this is a yield. And so we're talking about how many photons do I get out for every photon that I put in? That's essentially what we're looking at, right? And so what's my return on photons? How many photons fluoresce for every photon absorbed? It's given the symbol phi. Do you say phi or phi? What did Dr. Arrington say?
You said P.
Yeah. Okay. So phi, our quantum yield, is the rate constant for fluorescence. divided by the rate constant for fluorescence plus the rate constant for all of the non-radiative transitions. And so the only thing our molecule can do is either fluoresce or do something else that doesn't give off light, right? These are the only two options. And so we look at the fraction of that is fluorescing, and that is our quantum yield. Anthracene, the one we just looked at, which is the 3 fused rings. You don't have to draw it if you don't want to. Has a fluorescence quantum yield of 0.28. And so for every 100 photons you put in, you get 28 photons out. Quinine, which if you've ever put tonic water under black light, you've seen quinine fluoresce. Quinine has a fluorescence quantum yield of 0.59. And then fluorescein, which is based on its name, it should be a real good fluorescent molecule, right? Let's see if I can spell it. Fluorescein has a quantum yield of 0.89. And so, this quantum yield tells us how good it is going to be as a fluorescent molecule. We have uses for these. Maybe you want to tag a protein or something. You want to stick a molecule onto a protein so that you can watch it move through a cell, right? You shine a black light on it or some excitation source on it. You can watch that fluorescent bit move through a cell. And so you want to choose a molecule. You want to choose a tag that gives you pretty good return on your investment in terms of inputting some excitation photons and getting out some fluorescent photons. So the higher the quantum yield, the more fluorescence you'll see. Fluorescence is one of the techniques that's really useful for single molecule detection. We talked yesterday in lab that you are detecting against a black background, right? Because our light and our detector are perpendicular to each other. You're detecting against hopefully nothing, right? Hopefully against a very black background. And so all you need is one photon or just a single photon reaching a very sensitive detector, and you can see a single molecule. Of course, the better our molecule is at fluorescing, the more likely it is we're going to see it, right? Again, if we shine 100 photons on anthracene, we're only going to get 28 photons out. If we shine 100 photons on fluorescein, we're going to get 89 photons out. And so we're more likely to see the fluorescein molecule in a single molecule experiment than we are anthracene. All right. We talked in the last chapter about the lifetime broadening in AA, right? And so that lifetime broadening is due to the timeline, the lifetime of that transition. And so the lifetime tau is equal to 1 over these rate constants. Right? So again, 1 over the rate constant for fluorescence plus the rate constant for all the non-radiative transitions. Now those rate constants are not always easy to determine, right? But we have another way of figuring this out. We can look at intensity. So let me see. This, right, is our lifetime. These are our rate constants. For the fluorescence. And the non-radiative. Another way we can look at this is the intensity is related to this lifetime. The intensity that we measure, I, is equal to the initial intensity times E to the negative time, so the actual time the experiment's going on, over this lifetime, tau. Right? So I and I naught are intensities. T is time. And again, tau is that lifetime. And so how we would determine lifetime using this equation is we would have our excitation source on only for a brief period of time, right? If we're using laser sources, there are pulsed lasers that have times of 5 nanoseconds, some are even shorter. And so you just shine the light for a very short period of time, and then you measure the fluorescence afterwards. Remember, we talked in chapter 2 when we first did the Jablonski diagram that fluorescence lifetimes can be very, very short, right? On the order of nanoseconds. And so if we shine this light for 5 nanoseconds, we got to measure it quickly to see how that fluorescence decays. And so if we're looking at intensity versus time, we expect to see, since there's an E here, right, we expect to see this logarithmic kind of decay in intensity. And so this is our I naught, right? As we measure our intensity, we can fit this curve to find the lifetime. So that helps us if we don't know those rate constants for fluorescence in the non-radiative transitions. All right. So we want to have good fluorescence intensity. We want to make sure that we are sort of pulling out all of the photons that we can out of our molecule. And so factors so far that affect fluorescence intensity, well, one of those is going to be the quantum yield. Right. The higher that quantum yield, the better, the more fluorescence intensity we're going to get. Right. For whatever reason, our textbook uses F for power. Now, my guess is they're using F because we're talking about fluorescence power, but still it's a little funky in my mind. I'm going to stick with their notation, but know that F is just the power for the fluorescence. Right? I would have used piece of F, but they are using just standard F. And so, of course, F is based on our quantum yield. It's based on that initial intensity. It's based on this factor S, which is an instrumental factor, and that's going to vary from instrument to instrument. And so it sort of takes into account all of the losses that we see, you know, at surfaces that, like we calculated in chapter 3, all the losses that we see in the optics and the grading and the exit slits and the actual, you know, sample scattering, all that stuff. And so that's an instrumental factor that's constant for any instrument. Well, I should say for any setup, right? It might change if you change solvents or cuvette material or something like that. Often when we look at fluorescence powers or intensities, we report it in what we like to say are arbitrary units, right? It doesn't matter what the units are, we just report it. The other thing that we sometimes do is look at relative intensities. And so in either of those cases, we don't really need to know S. In the arbitrary unit case, because who cares what the units are, it can roll S into that if you want to. And then in the relative case, right, if we're going to look at this relative, if we're going to do division to find the relative intensities, then the S will cancel out. And so often we don't need to know S, but it's good to know that it is there. And then 1 minus 10 to the negative epsilon b c. That looks familiar to us, right? That's Beer's law. And so it depends on the quantum yield, how much we get out. It depends on the absorbance, which is how much light it actually does absorb at a given wavelength. And so all of these things come into play when we start talking about fluorescence intensity. And then I naught is the power of the excitation source. There's a question, a homework question that deals with using this equation, right? But you can see that as the quantum yield goes up, the intensity goes up. As the power of the excitation source goes up, the intensity goes up. And this piece here is a little harder to see right offhand, right? But if we had 1 minus 10 to the negative 0.05 versus 1 minus 10 to the negative 0.5, who's got a calculator / a phone handy?
Would the second one be bigger?
Yeah, I sure hope so. Right. Did anybody find some numbers?
The top one is 0.1087.
Okay.
Bottom one is 0.6838.
Yeah. And so because it's this exponential value, it doesn't go linearly, right? If we multiply, if we increase absorbance by a factor of 10, we don't get an increase of 10, but we still get a major increase in our overall power based on increased absorbance. So increasing all of these 3 quantities will help us increase the fluorescence intensity that we get out. if we have some negligible absorbance, in other words, if our molecule is not great at absorbing our light source, right? Then we can simplify this. And so if we have relatively low absorbances, this 0.05 that I mentioned earlier, then we can sort of turn this into a constant or a series of constants, and we get F is 2.303 times phi I S epsilon BC. Now, in my opinion, that's not a great time saver, right? And because it only works in this very limited series of this very limited absorption range, and you know, it doesn't save you a whole lot of number crunching. You still need to know all of the pieces. You just don't need to know 1 minus 10 to the. And so this is, it uses a Taylor series approximation if you're a mathy person. And so it, you know, might save you a little bit of time, but it's not super helpful from my perspective. All right, one more thing that can affect the intensity that's not in this equation. So between the molecule that's actually fluorescing and the detector, lots of stuff can happen. Right? But also we can have, as that interactions with that molecule that can prevent it from fluorescing, right? So if our quantum yield is 0.59, like it was for quinine, if we put something in our solution that causes it not to fluoresce, we call that a quenching agent or a quencher, right? And so quenching is this process of reducing fluorescence. And so we can reduce fluorescence in a couple of ways. Give me one of them.
Is that by scattering?
So that would reduce how much of that fluorescent light gets to the detector. But let's say that our molecule has absorbed a photon, and we're not actually thinking about the detector. We're just thinking about that molecule giving back off light, right? What could prevent it from giving off light?
Low quantum yield?
Yeah, if we lower the quantum yield somehow. And so what would have to change in this equation for quantum yield in order for it to get smaller?
A high rate constant for the non-radiative events?
Yeah, if our rate constant for fluorescence goes down and our rate constant for non-radiative goes up, that's going to give us a higher, a lower quantum yield. And so this reduced fluorescence is really due to a reduced quantum yield. And so we need to increase those non-radiative events. There's a couple of ways that we can do this. Right? One of those non-radiative events is well, the vibrational relaxation, right? That's a big non-radiative event. And while we talk about it mostly within excited electronic states, we can have vibrational relaxation all the way from S1 to S0, right? It can just vibrate and lose energy and vibration all the way from S1 to S0. In order to do that, it needs to be moving a whole lot. And so if we move a whole lot, what's our temperature going to be? High. Thanks, Abigail. Yeah, so an increase in non-radiative events could be things like, let me change colors here, increased temperature. What's that really doing? P-chemists, everybody here has had or is in P-chem except for field. And so if we increase temperature, what's happening to those molecules in our system?
Moving around a lot faster.
Moving around a lot, and what's happening in between them?
Collisions.
Collisions, yeah. Increased temperature, we increase collisions. And if I increase my collisions, I'm more likely to give that energy to a molecule in that collision than I am to fluoresce it out as a photon. Right? So there's that collisional energy transfer. You can have other molecules or solvents. So I'm going to say there could be other species. That are very good at sort of either limiting the change in your electronics state, right? Remember we talked about from S0 to S1, there's a shift in that electronic structure. And so there are molecules that can either make that shift greater so that you change that quantum yield, or make it slightly less, right? Either case could shift that quantum yield to a lower. It could shift it higher, but it could shift that quantum yield lower. And so other species may affect I'm going to put Frank Condon overlap. Okay. And so as those other species interact with our molecule of interest, oxygen is especially notorious for this, right? If you're doing a fluorescence experiment, you want to purge your solvent of oxygen because oxygen is real bad about shifting real bad about quenching fluorescence. Yeah, and so there's also just there's something called resonant energy transfer. And so if you have another species that's in solution that has a similar energy gap as to your molecule, then instead of fluorescing, that molecule could just transfer that energy to the other species. And that molecule might fluoresce, but it's likely that it's not going to fluoresce at exactly the same wavelength. And so you're not going to see fluorescence from your molecule of interest. You can calculate sort of quenching constants and things like that. We had to do that in graduate school. I think I've told some of you we did laser spectroscopy in this weird group at Purdue, and a lot of what we did was fluorescence-based techniques. And so you put in a photon or two, and you want to make sure that you get a photon out. And so you want to increase your quantum yield. So we had to make sure that our solutions and our environments were free of these quenching agents, and free of anything that could absorb that energy from our photon. And so they do have some quenching is a big piece of fluorescence. If you move into research and things like that, you got to pay attention carefully. We will save molecular structure and the instrumentation for Friday. Those of you who were in lab yesterday, if you would, share your data with me so I can send it off to those of us who weren't in lab yesterday. Again, just those absorbances, as well as what your 4 solutions were made of, is really all that I need to pass along. So if you have that at some point today, send it to me so that I can share it. I hope you have a good Wednesday. Be well.